Welcome to the deep dive. Today we are really strapping in for something special. We're taking a look at DIY engineering,
hmm
where scrap metal, it doesn't just get recycled, it gets, well,
Yeah,
promoted.
seriously upgraded.
Exactly. This isn't just about cobbling something together, it's about solving a really specific problem. How do you get precision when your budget is basically zero?
Right.
So we've got these sources detailing how a handmade column drill, you might call it a drill press, was put together. The creator is known as Mr.Dr.Moradi.
Okay.
And here's the kicker, the big claim. He says this project saved him, or maybe created, 10 million Tomans in value. That's quite a number.
It really is.
Yeah.
That 10 million Toman figure, it grabs your attention, doesn't it? It tells you straight away, this isn't some wobbly, barely functional homemade tool.
No?
We're talking about something aiming for and apparently achieving real accuracy, workshop grade, big from practically nothing.
Right.
So our mission for you, the listener, is to unpack that. How did he do it? What were the material choices, the clever design tricks?
The hacks, maybe?
Yeah, the engineering insights, really, that let him take low-cost scrap and turn it into something that valuable and precise.
Absolutely. Because you usually think precision tools need precision materials, expensive stuff. But key takeaway here, I think, is that Mr. Dr. Moradi shows how smart thinking, smart engineering, can beat expensive materials, how you can solve big problems like structural wobble really cheaply.
Exactly. Ingenuity over budget.
Okay, let's start at the beginning. The frame, the actual skeleton of this machine, what's it made of?
Just standard water pipes.
Seriously, like plumbing pipes.
Yep. Strong, easy to find, and most importantly, incredibly cheap, especially if you get them as scrap.
Right, that's step one in keeping costs down. Use common materials.
But it gets better. Look at how he measured the base.
Okay, yeah. The sources say for the base structure, he used two main pipes, and they were each 39 centimeters long.
49 centimeters, not 50.
Exactly. And apparently when asked why 49, not a nice round 50, his answer was basically, no reason.
Huh. I love that.
It was just an arbitrary cut he made. It's so relatable, isn't it? That little imperfection.
It totally is. And it speaks volumes about practical making versus, textbook engineering.
Yeah.
Sometimes good enough is actually perfect. If 49 works, why waste time getting it to exactly 50? You move on.
Move on to the next problem, which was clearance, right? How much space between the drill and the base?
Yeah, the working height. He set the drill 15 centimeters up from the base,
And why 15?
specifically to fit larger workpieces underneath. He wanted that flexibility.
Makes sense.
But he also noted, that 12 centimeters probably would have been fine for most of the smaller jobs he does in his repair shop.
So he thought about it balancing the ideal 15 centimeters with maybe saving a tiny bit more material, 12 centimeters.
Right. He chose function, but it wasn't over-engineered. It was a conscious choice.
Okay, now the tricky part, the vertical movement, making the drill go up and down smoothly and accurately, that's what makes it a drill press.
Indeed. For the main column, the outer structure, he used a slightly larger water pipe. And inside that, the two smaller base pipes could slide up and down. That's your basic vertical motion. And those inner sliding pipes, they were about 12 centimeters long.
Wait, why two inner pipes sliding? Why not just one?
Ah, that's crucial. That's the first really clever bit for stability.
Okay.
If you're building a drill press, that up and down movement has to be perfectly straight.
Yeah.
No wobbling side to side, no twisting.
Right, or your hole ends up in the wrong place.
Exactly.
Yeah.
If you only had one sliding pipe inside the larger one, there'd be nothing to stop it from rotating slightly or shifting left and right. That's lateral movement, and it kills precision.
Got it.
So by using two inner pipes sliding together,
They keep each other aligned.
precisely, they create 2 points of contact within the outer rail. It mechanically locks the movement into one single vertical plane. It prevents rotation. Simple, cheap, but solves a huge problem in constraining the motion. Without that, you might as well just use a hand drill.
Okay, this next part is where I think Mr. Dr. Moradi's creativity really kicks in. Raising and lowering the drill smoothly requires, mechanical advantage, right? Gears or levers.
Usually, yes. And that can mean custom machining, which costs money.
But he didn't do that. He looked, elsewhere for parts.
He looked at a bicycle.
Get out of here.
Seriously, the core mechanism for that fine up and down movement, it uses standard bicycle components, a bicycle hub, the center part of the wheel.
Yeah, the tupidosharky as mentioned.
Right. And its spindle, the axle or mill. He repurposed those.
Why bicycle parts? What's so special about them?
Well, think about it. They're designed for smooth rotation under load. They're mass-produced, so they're cheap, they're durable, and they have really tight tolerances built in.
Ah, okay. So he gets pre-engineered precision for pennies.
Exactly. He's leveraging the known quality of a bike hub for his drill press. He didn't have to invent that mechanism, he just adapted it. It saves a ton of design and fabrication effort.
Clever. But how does rotating a hub make the drill go up and down?
He needed to translate rotation into linear motion. So he built a simple pulley system.
How?
He took the spindle, that axle part, and welded 2 washers onto its end. Boom, instant pulley or Corgora.
Okay, simple enough.
And what runs on that pulley? A standard bicycle brake cable, the Tomans,
Right. Okay, so the cable wraps around the spindle pulley.
and pulls the drill assembly up or lets it down. But here's the really smart bit, showing he was thinking ahead.
What's that?
Cables stretch over time, right? Especially under tension.
Yeah, it happens with bike brakes all the time.
So that stretch would eventually introduce slack into the system, making the movement less precise.
Okay.
So he built in an adjustment screw, a pitch réglage, right at the top of the mechanism.
Ah, like on a brake lever.
Exactly the same principle. If the cable stretches, you just tighten that screw a bit, it takes up the slack, and restores the tension and precision. It's built-in maintenance. Foresight.
That's brilliant. Shows he wasn't just slapping it together for a quick fix.
And we should remember this wasn't his first try.
Oh, right. The sources mention some trial and error.
Yeah, his initial idea for the vertical movement was apparently quite different. Something involving welding a bicycle chain onto one of the pipes.
Like a rack and pinion system?
Sort of, yeah. But it didn't work. Probably impossible to get smooth, precise movement that way with scrap parts.
So he failed but didn't give up.
Exactly. He pivoted, ditched the chain idea, went for the reliable, proven rotation of the hub and spindle. That persistence, that willingness to iterate, that's often the real difference maker.
Okay, let's shift focus to the absolute deal breaker for any drill press.
Yeah.
Accuracy. If it drills wobbly holes, it's basically useless, right?
Absolutely critical. And Mr.Dr.Moradi hit a major wall here.
What happened?
When he tried drilling really small holes, like 2 millimeters, maybe 3 millimeters.
Toony stuff.
Yeah, precision work. He found the drill bit had about 1 millimeter of uncontrolled movement. Wobble. The source called it chally.
1 millimeter. That's huge when you're drilling a 2 millimeter hole.
It's disastrous. Half your hole diameter is just random slop. It makes the tool completely non-functional for accurate work.
So you've got this frame made of scrap pipes, a lift system made of bike parts. How on earth do you get rid of a millimeter of wobble without spending a fortune on precision ground rails and bearings?
This, for me, is the most ingenious part of the whole build.
Okay, I'm listening.
He didn't add expensive parts. He added a geometric constraint, a simple piece of pipe.
Another piece of pipe.
Yeah. He welded an additional small piece of pipe onto the fixed structure, position so it's just tangent to the moving part, holding the drill motor, just touching it.
Tangent, meaning just brushing against it.
Exactly. MoMAs, as the source might say.
Okay, I'm trying to picture this. How does adding one little pipe that's just touching fix a 1 millimeter wobble?
It's a clever mechanical principle called preloading. Think about why the wobble exists.
There must be tiny gaps, right? Between the inner sliding pipes and the outer fixed pipe.
Precisely. Mechanical clearance. It allows the moving part to rattle around slightly in that space.
Yeah.
By welding that tangent pipe in place, he created a constant pressure point. That little pipe is always pushing gently against the moving assembly.
Ah, so it forces the moving part against the opposite side of the main rail?
You got it. It takes up all that slack, all that clearance on one side. Instead of rattling between two surfaces, it's held firmly against one surface.
So the gap is still there, technically, but it can't move into the gap because the tangent pipe is holding it steady.
Exactly. It's like putting a permanent shim in place. It's passive resistance that maintains constant contact and alignment. It costs maybe a few cents in scrap pipe and a minute of welding.
And it solved the $1 million, or I guess 10 million to M in accuracy problem?
Pretty much. That tiny subtle addition is arguably the most valuable piece of engineering in the whole machine.
Mm-hmm.
It turned it from a wobbly toy into a precision tool.
And I love that little detail. The sources mention that the old, unused bicycle chain from his failed first attempt was still attached somewhere on the machine.
Yeah, like a little scar tissue.
A visible reminder that the path to success often involves hitting dead ends first. You learn from the failures.
Okay, let's bring it back to the money. That 10 million Toman figure.
Yeah.
We need to connect the dots. How does this ingenuity translate into that kind of cash value?
Right, let's ground it. First, the market comparison. If you, listening, went out to buy a new commercial column drill press with similar precision capabilities.
What are we talking price-wise?
Well, the sources suggest they start around 10 million Tomans, and they go up quickly, 12 million, 13, 15 million, even higher. So 10 million is like the entry point for a decent machine.
Okay, that's our benchmark value. Now, what did Mr. Dr. Moradi actually spend on materials?
Pennies, relatively speaking. The main material, the pipes, he bought as scrap Zayati.
Got it.
And we even know the price, 13,000 Tomans per kilogram, bought from a guy named Bagger.
13,000 Tomans a kilo. That's incredibly cheap.
So you compare that minimal material cost, maybe a few dollars worth of scrap metal and old bike parts, to the 10 million Toman value of a comparable new tool.
And the difference is staggering. He essentially took virtually worthless material,
Yeah.
applied his skills, his clever engineering fixes like the dual rails, the bike hub system, and crucially, that tangent pipe preload, and he created 10 million Tomans worth of functional utility. That's not just savings, it's value creation through know-how.
It's pure profit generated by smarts and skill, not by spending money.
And it helps to know a little about his day job, right?
Yeah, the sources give some context. He's not some specialized tool and guy maker. He runs a home appliance repair business.
Whereabouts?
In Mashhad, the address is mentioned, Nizam 24, Mohibi 28, Block 42. He fixes all sorts of household stuff, electric, gas, washing machines, microwaves, vacuums, you name it. And he focuses on using original parts for repairs.
See, that context matters. His whole professional life is about diagnosing mechanical problems in complex machines.
Right.
And finding cost-effective solutions using available parts. It's not a hobby. It's his daily grind. That mindset, that necessity is clearly what drove the ingenuity behind this drill press.
So wrapping up this deep dive, we started with just some water pipes and bits from an old bicycle. And through skill, welding, but maybe more importantly, through that relentless problem solving and clever engineering.
Like that tangent pipe 6.
Exactly. It became a high-precision tool worth a significant amount of money.
Yeah. And I think the big lesson here for you listening is that real innovation, real value creation, it doesn't always need fancy materials or huge budgets.
Right.
It often comes from seeing potential in stuff others discard. And then applying simple, elegant fixes to overcome the inherent problems, focusing on the geometry, the constraints, not just the price tag of the raw material.
It's about the thinking. So here's a final thought to leave you with, building on this whole story. If a high-precision machine, something valued at 10 million Tomans, can be built from scrap metal that costs 13,000 Tomans a kilo, just by focusing on smart, simple engineering fixes, well, what expensive, specialized tool or even service in your own life could maybe be demystified, simplified, maybe even built or fixed yourself using clever thinking and low-cost local resources?
Makes you think, doesn't it?
Yeah.
The knowledge, the ingenuity, that's the real value, not the shiny new material.
Definitely something to chew on.